Good afternoon, everyone. Thank you for joining this technical webinar. Today, we are very pleased at NLFEA to welcome two of our most experienced end users, Dr. Dennis Schoenmakers and Dr. Lex van der Meer. They both work for Wagemaker, a Dutch company. And we are very happy that they take some time to present some of their work. And today, the focus will be on the assessment of existing civil structures using nonlinear numerical techniques in Diana. So, in the name of the whole audience and the NLFEA, we are very happy to have them. For the one who are familiar with our webinar, you know by now that during the whole session, your microphone will remain muted. But there is a chat box and a question box. So if you have any questions, you can type that in this box. And I will keep an eye on the question box. And at the end of the session, if there are questions that are relevant for the whole audience, I will address them to Dennis and Lex. And then they will see if they can answer on the fly or eventually need more time and get back to you per email. The session will be recorded, and after approval of Dennis and Lex, we will put it on our YouTube channel. So probably early next week, it will be available on our YouTube channel. And having said that, I think we are good to go. So I'm inviting Dennis to unmute himself and to start the presentation. The stage is yours, Dennis.
Well, thank you, Jean-Claude, for having us, and thank you for the nice introduction. Welcome, everybody, and thank you all for joining this online webinar. My name is Dennis Schoenmakers, and the subject, as Jean-Claude already mentioned, is the assessment of existing civil structures using nonlinear numerical techniques. And this will be a dual presentation given by myself and my colleague Lex van der Meer. So my name is Dennis Schoenmakers, and I'm working for Wagemaker for about 15 years right now in the role of FEM specialist, but still with a strong focus on the existing structures and the reassessment of them. Before that, I did a PhD at Eindhoven University of Technology on the subject of fracture and failure mechanisms induced by mechanical connections.
My name is Lex van der Meer. Just like Dennis, I also did a PhD at the Technical University of Eindhoven. And we have been colleagues back then. And now since 1 year, I also work at Wagemaker. So we're colleagues again, and it's very nice to do this presentation together. After leaving TU Eindhoven, I have worked at several companies where I've always focused on finite element analysis, especially the nonlinear type. And it's very nice to be able to present about this at this occasion. So I want to give you a very brief introduction to Wagemaker, the Dutch company where we both work. It's located in the Netherlands, in Rosmalen, next to the highway A2. You see our office in this picture. And we specialize in the design and assessment of infrastructure. And we are also involved in engineering of new structures, but the focus of this presentation will be on existing structures, especially those assessments using Diana. How it works, that's very nice. So why is reassessment of structures necessary? The most important reason for that is shown on this slide. So you see a Dutch road with traffic on it about 100 years ago up till now. Well, you can see that the traffic has become much more intense, and also the individual vehicles have become heavier. So this is, of course, an important reason for reassessment, because the loads on the structures have increased over time. and that is not the kind of loading they were originally designed for. On this slide, we see in the bottom, I can pinpoint it, we see a graph where it is shown when the Dutch infrastructure was built. And we can see there that the majority of infrastructure has been built between, let's say, 1960 and 1980, up till now. But this also means that the current standard, which is the Eurocodes, it came a lot later than these structures. So also the design rules and the insights regarding structural safety, they have changed since these structures were mostly built. And then we see here, it's in Dutch, sorry, but I'll explain it a little bit. We see the replacement value of various kinds of infrastructure, and it will cost the Dutch government billions of euros if they need to replace all these structures. So I talked about the Eurocodes. In the Netherlands, we have for assessment of existing structures a special set of standards which is called the NAN 8700 series. And also for the primary infrastructure for which Rijkswaterstaat is responsible in the Netherlands, we have some dedicated guidelines from Rijkswaterstaat as shown here on this slide. And except for the heavier traffic and the changes in design rules, there can also be other reasons for reassessment, such as regular assessments that need to be done by the instancy which is accountable for the structure, but also if there is expected or suspected damage, and also, of course, if there are physical modifications done to the infrastructure, which often happens because the Dutch roads are very busy, so they need to be widened, for instance. So that was a bit of an introduction on reassessment and its necessity. And Dennis will now tell you more about Dapped-end beams, which you've just already seen. Well, I realized now that I somehow skipped one slide, but we will leave it at that, and I will give the presentation to Dennis, who will talk about Dapped-end beams.
Well, thank you, Lex, for this contribution and this nice overview of causes to reassess existing civil structures. So one type of these structures we use the Diana software for is to analyze the structural behavior of half joints or Dapped-end beams or notched beams, just how you like to call them. The picture shows a typical example of what in the Netherlands we call a so-called springwerk structure. So basically, this is the half joint with the notched beam on top of it, in between an elastomeric bearing, and it's supported by a cast in situ supporting structure, so to say. So this is the kind of structures we use the software quite frequently for. What's typical about these structures is different reinforcement concepts that have been adopted in time. Often we notice an inclined prestressing bar or a vertical prestressing bar, stirrups in the beams, diagonal bars to regulate crack width control in that throat of that beam. And sometimes we notice combinations, just like this one. This is a typical strangely bent bar, but it's used back in the day when they designed this kind of structure. And we notice that the reinforcement ratio in the beams is relatively high. This shear-prone zone is full of stirrups, while the supporting structure usually exhibit less reinforcement. Here we see another example of such a depth-end beam and a notch of a supporting structure. And what we frequently see is that the detailing of the reinforcement bars is rather poor. So this hook, we should preferably have this hook bent toward the other side to support that compressive strut that emanates from the elastomeric bearing, for instance. And anchorage length isn't that large either. So this is a rather short piece of anchorage. So it's questionable whether all reinforcement bars can be loaded to the stress level it is initially designed for. Due to this structural detail, a gap in between the beam's head and the supporting structure is present, so we need a joint. But joints are typically vulnerable due to leakage, which may result in damage due to the icing salts or road salts, which are dripping from the top side into this zone. So for one such a structure, we have made a nonlinear finite element analysis using the Diana software. The right-hand side shows a fragment of that original drawing. So in this case, we got a vertical pre-stressing bar, a diagonal bar to properly reinforce that throat, that vulnerable part of the beam. And we got lots of stirrups, and we got a cast in situ slab on top of it, as indicated by the green parts, the mesh visualization of the structure. And the beam's structure at its ultimate load is given in the figure below, the crack state. So we have observed large cracks in that re-entrant zone of that notch, as well as bending cracks. And here you can see obviously the effect of inclined pre-stressing bars, which arrest the cracks, so to say. Due to the building sequence, we used a structural nonlinear phased analysis to take into consideration the building sequence as set. So in the first phase, we load the model by its dead weight and the pre-stressing of the strands. And in this phase, the beam is continuously supported to simulate the influence of formwork. And in the second phase, the beam was installed on site and mounted on elastomeric bearings. So this is what we are seeing on the left-hand right here. And the final stage, no change in supporting conditions, but the green part is activated, including some stirrups. So model validation is always an important part. So we started with checking whether the pre-stress loading was successfully adopted in the model. So as we expect from a prefabricated beam, the pre-stressing stress at the beam's head is 0, and it gradually develops over its anchorage length to the maximum. So this one looks okay. During that phase, the vertical debiduct bar, the pre-stressing bar, was stressed by nodal loads as well. And in the subsequent stage, the anchorage bearing plates were attached to the debiduct bar using a master-slave formulation of nodal displacement. And here we see some details of the structure itself. Apparently, we have loaded the bar to a maximum stress level of approximately 550 megapascal, which is correct. And due to that pre-stressing load, a compressive stress field was introduced as indicated on the right-hand side. And perhaps you are questioning why the top side is much higher loaded than the bottom side. But remember, this was a T-shaped girder with a bottom flange. So obviously we should find a pressure that is higher on the top side than it is on the bottom side. So this looks satisfactory. And the reinforcement was modeled as embedded, but also as bond slip relations. In this figure, we notice there's a more detailed view of that notch beam with different types of bond slip relations adopted in the model, indicated by red, green, or yellow bars. So basically, due to the development of shear stress between the bars and the surrounding concrete material, slip develops, which may result in a rather ductile behavior or a rather brittle behavior, and which bond slip relation according to FIP model code should be used depends on parameters such as concrete strength, diameter of the rebar, coverage, and location of the reinforcement in the mother element, etc. So lots of combinations are possible, as you can imagine. Here we see some detailed views of the notch when it is reached its final failure load. On the left hand side, the crack width, so it's a rather large crack of 3.5 millimeters. And on the right hand side, we notice an apparent compressive strut which emanates from the bearing block over here towards that anchorage plate of that divider bar. And for reference purposes, the corresponding archive drawing is given in the middle, so you can place some perspective to it, so to say. Obviously, to come to that crack width of 3.5 millimeters, we should increase the stress level, the loading level in the model. So in this slide, we show 4 detailed close-ups of the crack width development with increasing load levels. So at first, the damaged state is rather limited, and with increasing loading levels, the damaged region is growing up till that final value, as we've shown over there. The nonlinear response is given as a load deflection diagram and looks something like this. And in this case, we used this specific point as the monitor point, and I plotted vertical displacement. It's in Dutch, but I will translate: vertical displacement and total load in the model. And the convergence characteristic looks like the figure on the right hand side. So up to about step 36, the model runs quite smooth. Nothing typically happens except some development of cracks, but apparently these cracks don't affect the convergence rate of the model. And after step 37, we notice bad convergence or no convergence at all. So in this simulation, we recognized load step 41 as our ultimate loading level. So that's about it about the Dapped-end beams. So I guess these few slides and gave a nice glimpse of how we used the Diana software for this type of structures. Now will Lex take over, and he is going to talk about box-girder bridges and creep and shrinkage deformations.
Thank you, Dennis. That is indeed the subject I would like to tell a bit more about. The box-girder bridge that is shown on this picture on the top left is currently being assessed by us within the combination NLFEA Wagemaker as part of a big assessment campaign by Rijkswaterstaat. And this is a bridge in the Netherlands spanning the river Maas, and it has a main span of about 140 meters. The box-girder has 2 cells, as shown in the middle picture here. And the height is between 3 and 6 meters, the height of the cross-section. This bridge was constructed around 1975 and is made of normal strength concrete. And it has a lot of prestressing inside, both in longitudinal, transverse, and vertical direction. For this particular bridge, a global assessment is being done by other colleagues, and with Diana, we particularly focus on the creep and shrinkage, which I will present about now. And currently, I'm busy doing a assessment of the transverse walls inside the box-girder. So with these kind of structures, it is important to recognize how they were originally built. We call them, in English, balanced cantilever bridges, because they started building these bridges from one pier, and they put a piece of concrete which is called the hammerhead on top, and then segments are placed gradually on each side until you get 2 very long cantilevers. And this is also done from the other side of the river until they almost meet. And then closing segments are placed here in the mid span that you see in the top image, and also near the land connections, and then a continuous structure exists. Another important factor is that the permanent load is very large in these bridges, about 80% of the total load, and that is also why we put a special focus on creep, because of the high contribution of the permanent loads. And why this is important is because the pre-stresses inside the bridge and the pre-stress losses, they are affected by creep and shrinkage of the concrete, and also by relaxation of the pre-stressing steel. And eventually the amount of pre-stress that exists after a lot of years of time-dependent losses determines the structural capacity. By the Technical University of Delft and TNO, a Dutch company that does a lot of research on, among others, concrete structures. It was found that the existing models from Eurocode and Model Code, they underestimate long-term creep and shrinkage, especially if you go to several decades. And RILEM developed a new model, which is called RILEM V4. And they also found that this new model fits better with the measured deformations in several of these kind of bridges. So for this particular bridge, we also used the RILEM V4 model for modeling the creep and shrinkage of the concrete. Now the Ryland B4 model, I'm not going into a lot of detail about it, but it has input parameters related to concrete mixture, aging of the concrete, environment, such as temperature and relative humidity, and also the shape of the structural elements. And this is especially related to the effective thickness, because for the drying part of creep and shrinkage, the effective thickness affects the rate of creep and shrinkage. So the thicker structural elements, they creep and shrink slower than the thinner structural elements, which is shown here in the graph on the right. And this is particularly important because the floor of the box girder, it changes a lot in thickness. So it is around 1.15 meter effective thickness above the pier support, and it's only 0.3 far away from that. So we built a Diana model for this bridge, but not of the whole bridge. There is already a model for the whole bridge in other kinds of software. In Diana, we focused on the part of the bridge which is built as a balanced cantilever bridge. We modeled in a simplified way the phasing of this bridge. And we did first the building phase when it's still cantilevering. And then after that, we put the supports and the closing segments. And in the mid-span, we put symmetry conditions so that it actually represents the whole part of the bridge spanning the river. So for doing models of this size and with these kinds of structural element thicknesses, it's not necessary to make a full solid element model. So we decided to go for curved shells, which we call 2.5D. This works fine, actually. There's some consideration that should be paid to the overlaps in these shell elements, not only regarding the actual weight and inertia of the structure, but also regarding the embedding of pre-stressing cables, which I will come back to at the end of this presentation. So the modeling of the pre-stress is quite some work. We have very detailed archive drawings of the layout of these cables, as well as a lot of cross sections. So all this information from the drawings needs to be translated somehow to coordinates, which we did in Excel. And then we use a Python to generate the pre-stressing tendons, or in this case, bars in Diana. And here you can see what the cantilever pre-stressing looks like, which is already present in the first phase, the building phase of this bridge. And then on this slide, we can see the continuity pre-stressing at the left side span and in the main span. And this is the pre-stressing that is actually post-tensioned after the closing segments have been placed. And then for the creep and shrinkage, I already mentioned before that the effective thickness is relevant for the which creep and shrinkage curves to use. And we distinguished 8 different curves, which are the colors in the Diana screenshot that you see here. And so depending on the effective thickness, the structural elements get assigned their own creep and shrinkage functions. And what we did is we made an Excel sheet with the Ryland V4 model, and then the various curves are generated with that Excel sheet and read with Python into Diana. And the Diana translates the creep function actually to a Kelvin chain. And in the out file of Diana, you can see what parameters are actually used in the Kelvin chain. And what is very important is that you do a single element test where you test whether the creep function in Diana works as you actually would expect from theory. Well, you need to validate, of course, somehow. And luckily, we had deformation measurements of the bridge available. And they have been recorded regularly since 1975, after the bridge was closed, until 2 years ago. And they are still ongoing, I assume. So what we can see here is with the red curve that our Diana prediction with the Ryland B4 creep and shrinkage model shows reasonable agreement with the measurement data. It's a little bit on the conservative side, which is actually good for the structural safety. And after this validation, we actually compared the section forces and moments of our Diana model with Ryland V4 creep and shrinkage after 100 years to another model in SIA Engineer, in which some simplified assumptions were done regarding creep redistribution and regarding time-dependent pre-stress losses, as shown on this slide. And what you see here is the normal force in the model after 100 years of both models. And we actually found pretty good agreement between both models. And we did the same for bending moments. And we found also a very good agreement. So we were convinced that after doing this more advanced analysis, that the simplified model and assumption that were done there were in this case good enough, and it was not necessary to refine the time-dependent pre-stress losses that were put into that simpler model. And now my colleague Dennis will again continue and tell you more about the historical structures in the city of Amsterdam.
Thank you, Lex. That finite element model was quite a nice one, I think, with lots of pre-stressing bars. If I can remember, it's more than 700 in total. So nice overview of what you have done. As Lex mentioned, also historical bridge structures, such as those in the city center of Amsterdam or Utrecht or 's-Hertogenbosch, are subjected to judging the structural safety as well. These structures determine primarily the street view and the historical character of the city center. So in this perspective, retainment is crucial, I would say. On the right-hand side, we see a finite element model of such a structure. What's the problem with this kind of structures is that often they were designed more than 100 years ago. Not all of them, but mostly they are rather old. But they are nowadays loaded in this way. So heavy truck loading is necessary for the city center, and now these structures are loaded to lots of more load than originally was intended. Here we see some fragments of archive drawings of a bridge lying in the Grachtengordel in Amsterdam. And what's apparent of this figure, as indicated in the model picture as well, is that actually the largest part of the structure is beneath ground level, so it's hardly visible. But that part in particular is important for the structural capacity of the arch-like structure in total. So we made a three-dimensional finite element model in Diana, as shown in the figures on the left. The model consists of several different segments, different parts. And the final mesh again looks like the figure on the right-hand side. In this model, we used solid elements to simulate the true behavior of the bridge deck, which in fact is rather stocky, right? So it's nor a beam nor a shell. It is a solid, so that being a solid should contribute to the load distribution in mainly the lateral direction. So that's the reason why we have chosen to use the solids in this case. Some horizontal soil loading was modeled using a spatial function due to the presence of the water level. A swap in pressure is present. So with a spatial function, it's rather easily and convenient to model all these surface loads, because yeah, these walls are all skew and inclined toward each other. So that's a convenient way, I would say. I definitely would recommend it. And the model was loaded by a traffic load according to Eurocode. So basically, it's the load model which is also used to design new structures. But the loading effect introduced by the heavy truck given in the picture should be covered by this load model, I would say. On the right-hand side, we see a load model 1 tandem system in the middle of the bridge deck, and this was modeled using quadrilateral loading, which don't affect the finite element mesh. Some pictures of the deformed shape under non-symmetrical loading situations are given in this slide. Non-symmetrical loading situations are for this kind of structure most critical. So that's the reason why we have chosen to use them for presenting the deformation modes. So as a model, the real three-dimensional deformations that developed were satisfactorily modeled, and hence load distribution was also. Usually, yeah, these structures are modeled using shell models, but in this 3D solid element modeling showed some real benefits to comprehend the actual behavior of these types of structures. Still, it's a linear elastic model, but we thought it was a nice project to share some slides with you. So now Lex will take over and will continue with an investigation into modeling pre-stress post-tension loads in Diana.
It seemed like a good idea to also present some modeling challenges or lessons learned, as I assume other Diana users will be listening. So what you see here in the bottom is another archive drawing where you see the layout of pre-stressing cables. And at the top, you see a side view of a Diana model. Well, if you put these curves in Diana, or put these individual tendons in Diana, you want to do it as accurately as possible. At least the centroid at each location should match the archive drawings, but preferably the actual location of the cables should be as realistic as possible. So if you want to translate such a drawing to a model, then you have several options in Diana to model the curve. Polylines, which are piecewise straight curves, which are actually in the background modeled as cubic splines through points, circular arcs, and straight lines. And you can also, using the Python command join wires, use a combination of these. My question was, does the shape affect the friction losses when a post-tensioning load is added to the modeled reinforcement geometry? And a little spoiler alert, yes, it does. So what you see on this slide is a test model, and the same shape of prestressing cable is modeled in 4 different ways. The top one is the reference one with circular arcs. Then the one below that is a curve where we just took a regular spacing of points and calculated the coordinates and used those points for the curve. Then the third one has a local modification of the points near the intermediate support. And the bottom one is similar to the second one, but it has each point moved in vertical direction by plus or minus 10 millimeter. So 10 millimeter on the length of this cable is seemingly very small. But if you look at the results, you can see that the first 3 models give more or less the same result. So what you see here is the pre-stressing force in the cable after direct losses. So that is losses due to retention length, which is put to 0 in this case, and wobble and friction. But we see also that for the cable that has points alternatingly modified by 10 millimeters, that there's a lot of additional pre-stress loss due to friction. And we see it here also in these graphs. So the cable shape to the eye, and also in this detail here, looks almost similar. But then the results for this last variant is very different. And this test model was actually inspired on a real case where we experienced this same problem. And that's shown here. And we have here in red, we have a reference calculation using different software. And let's say a rationalization of the cable shape. And we see that in Diana, if we use a polyline, which was not included in the test model I just showed, but the polyline is piecewise straight. And if you have no continuous curvature in your cable, then Diana will not calculate any friction losses. It will just calculate the wobble effect. Then using the curve in Diana, through all the points that we took from the archive drawings, we arrived at about 10% less pre-stress in the middle, which was unfortunately also the zone of interest for this model. So we were not satisfied with this big difference. And we tried then to make a curve in Diana which is piecewise, so going using a curve, but only through 3 points at a time. Well, that went a little bit better, as we can see from those two results. But as it turned out, if you have a lot of points and a cable shape which is a little bit suddenly changing direction, then it's very hard for Diana to make a cubic spline that goes through all the points and is not oscillating between those points. And what you see here is we used SciPy, a Python package, to make a smoothed spline. So that's the same kind of spline as Diana makes, but with a smoothing parameter. And that means that it doesn't have to go exactly through all the points that you specify. And that smoothed spline, if you take the first derivative, it's well, much better, because the blue one is what Diana would do. So a lot of oscillations of the first derivative, which is actually the angle of rotation. And the green one is the smoothed spline, which is much more smooth. So what we did is take the points from the smoothed spline back into Diana, and that resulted actually in the black dotted curve, which is much closer to the reference analysis. And the orange one is the same, but also taking the horizontal curvature into account, which the reference calculation did it. So that is maybe more realistic, but a little further away from the reference calculation, because it's comparing apples to pears. So this is a very important finding for us, that you need to carefully consider how you model the reinforcement with post-tensioning loads in Diana. And after this problem was solved in the same project, we found out that if you use these kind of reinforcements with post-tensioning loads and combine them with curved shells, then it's very important to properly embed the reinforcement in the shell elements. If you let Diana decide, then you get this result at the top, and you see that at the location where the prestressing cable is going through the top of the wall, or maybe the floor, there's a lot of disturbances. I guess it is embedded randomly in either the wall or the deck, and similar here and here. So then I modified the cable shape slightly so that it would fit into the Diana geometry of the walls, and that solved luckily the problem. So this is what I would like to end our presentation with, a little warning of and some lessons learned regarding reinforcements in Diana with post-tensioning loads. And that was our full presentation. Also on behalf of Dennis, I would like to thank you all for attending. And I will give the word back to Jean-Claude.
Thank you, Lex, and thank you, Dennis, for this very nice and extensive presentation. There is a lot of positive comments to thank you and for the great work and the great presentation. So, yeah, in the name of the audience, I would like to thank you for your contribution to this technical webinar. There are a good number of questions, gentlemen, but they are very detailed questions. And maybe because of confidentiality on some of the project, you don't want to expose some of the information. So I'm not going to raise the question live. I'm going to share with you the question per email, Lex and Dennis. And then you will be free to answer directly to the person or to share some information. But I mean, people are very interested in your work, and especially in the bridge assessment. So that's interesting to see. And I mean, they are very happy with your presentation and the quality of your work. So that's the main message that I can share. But for some of the questions, I prefer that you get it by email, and then you evaluate at the company level if you can share some information. I think it's the best way to handle this type of question. So I will let you know the question after the session, Dennis and Lex. So I'd like to thank you one more time at the name of NLFEA and also from the large audience. I mean, there were a good number of people online today, and definitely with a lot of interest. I cannot read all the positive message, but a lot of people are saying thanks a lot for the presentation. Thank you for the great work and very nice work. So a lot of positive feedback, but also a lot of interesting questions. So I will share that with you. So Dennis and Lex, again, one more time, thank you all for your presentation, and thanks to the audience. I know that some people have quite a time difference, and still they are online, so thank you for that. And for the one who have been asking questions, as I mentioned, I will share them with Lex and Dennis, and they will review the question, and they will eventually get back to you if they think that they can share the information. You all, bye.